The topic that we have to do today or look into it is latent heat.
Like we've covered latent heat. Is the like energy that's not visible in temperature change once the substance reaches its melting
Actually,
boiling
the
point.
the next topic that I'm going to start is actually going to start from this point, so I'm just revising.
Okay,
Okay,
okay.
all right. So, latent heat would mean the energy required to change the state of an object. So, changing the state would is a general term, and it would mean that it could be anything, right? So, from solid to liquid to gas, all of these changes in state would mean that the amount of energy required to bring about this change will be found in latent heat. And similarly, if you remove that energy from the system, then it will start cooling down. Yes, and even then, in those cases, that would also be called as latent heat. Now, when you convert or when you move between solid and liquid, this is known as latent heat of fusion. And when you move between liquid and gas, this is known as latent heat of vaporization. Okay. Previously, in your old syllabus, this was referred as LV and this was referred as LF. Now they've made it general and they just write down small l. In my lesson or in my discussion, I would be writing down LV and LF so that we understand what type of latent heat is taking place at what stage of the procedure or the process. But in books or in marking schemes or in the examination questions, you will find that this is just represented as simple L now. Okay, so let's say that we have to heat up water, for example, from 20 degrees centigrade up to a temperature of 150 degrees centigrade. Now 20, 22, 25 is expected to be room temperature, right? And we want to take it to 150. And I understand that the boiling point of water is 100. So at that stage, there should be some latent heat required to change it from liquid to eventually gas. Now, for that, there will be some values given to you in the question, and let me write those values down. So, the specific heat capacity of water is given to you as 4200 joules per kg degree centigrade, of gas or steam is given to you as 2100 joules per kg degree centigrade. Latent heat of fusion is also given, and vaporization is also given. Now you have to be intelligent about this, what value you choose. Fusion is for solid to liquid when it actually melts. Vaporization is when it boils from liquid to gas. So let's say this value is 2.3 into 10 raised to power 6 joules per kg, and this is 3.3 into 10 raised to power 6 joules per kg. He may give you all the values to confuse you, but you have to be intelligent about this. So let's say that the mass of the system is given to us as 2 kg. Now let's break this down, that what's happening or what will happen if we heat it up from 20 and take it up to 150. So we start at 20 degrees centigrade, we keep heating it up. The very first time I will see that the temperature stops rising is 100 degrees centigrade. Why do I say that the temperature has stopped rising? Because now it is at its boiling point. Unless or until all the water in the substance or in that vicinity has boiled to become a gas or steam, the temperature will not change. And this is what we did in the last lesson as well, that latent heat. Okay, so the very first time we see that the temperature has fixed itself or it has stopped changing even though we are still heating it up, you will see that at the boiling point, right? So this is the stage when we will experience the latent heat being in action. So right now, whatever energy I am providing is not translating into heat. It's not translating into increase in kinetic energy of the particles, which eventually means the temperature of the system. What it actually is doing is that whatever energy I'm providing still to the system is being utilized to break the bonds between the atoms, because the substance has reached its boiling point, right? So now over here it was a liquid. Even at 100, water is still a liquid. But at the boiling point, we see that the temperature is still 100, but now it has converted into a gas. After this, we still keep on heating it up because the final target is 150 degrees centigrade. So we realize that this will eventually be 100 and then it will go up to 150 degrees centigrade. Why do we not see a change of state after that? Because boiling or becoming a gas is the final stage in the states of matter, right? So right now this is still a gas. Okay, now first we need to identify what formulas will we use to figure out the amount of energy spent to bring about this change in that system. I realized that the first stage is a change of temperature. There is no change of state. So I will use the formula of specific heat capacity, that is mc delta T, delta T representing the change in temperature. In the next stage, I see that the system only changes state, but there is no change in temperature. So I will use the formula ml, and to be more specific, I will write down mlv it would be, as vaporization has taken place, or you can say it's boiled now. Now in the last stage, we see that there is no further change in state available, or it's not going to happen again. So I also realize that there is only a change of temperature that I observe over here, so I will use the formula mc delta T. Now all of these formulas are basically Q is equal to mc delta T and Q is equal to ml, right? And these are actually going to calculate the amount of energy in joules for us, for the amount of energy that we may have spent to eventually find this, to eventually find how much energy would be required so that it increases its temperature from 20 up to 150. Now let's try to replace the values. So I'm going to write down Qt representing total energy equals to mc delta T plus ml plus mc delta T. And I'm going to mention that what each stage, this is from this stage, this is from this stage, and this is from this stage, right? Now let's replace all the values over here. The mass is going to remain 2 kg because that is, we are assuming that it's going to remain the same throughout the process. Then we have delta T plus m is 2, then we have to choose the value of latent heat, plus m is 2, specific heat capacity for the last stage, and change in temperature for the last stage. For the first stage, I see that this is increasing from 20 to 100, so that is basically 100 minus 20, or I can directly write down this is a change of 80 degrees centigrade in place of delta T. And in the first stage, I see that this is still a liquid, or you can say it is still water. So I should be choosing the specific heat capacity of water rather than the gas. So for the first stage, I will use the value for C as 4200, right? Let's move to the next part, that is the latent heat. Now, since it's vaporizing, or since it's turning from liquid to gas, I will not be using the value of fusion. I will be using the value of vaporization. The value of fusion is given to you to confuse you. It's not important. So I will write down the correct value over here. That would be 3.3 into 10 raised to power 6. You don't have to memorize these values. They will be given to you in the question. And the last stage, we observe that the change in temperature, that is for the delta T, is from 100 to 150. So I can directly write down that we have produced a change of 50 degrees centigrade, right? And over here we have the specific heat capacity of gas. So I will ignore the value of water and consider the value of gas. I will write down 2100, right? So notice that even though we may be using same formulas for the different stages, but for that specific stage, we will have different values because the state has changed, so their specific heat capacities or changes in temperatures might also be different. We would have to look for that in from the table or the values or the set of values that the question may give you. Now I'm going to take a pause at this point. I would expect you to calculate this value and tell me the answer, giving you 1 to 2 minutes for that. So the amount of energy that is required to bring about this change has been roughly found to be 19 into 10 raised to the power 6 joules, right? Okay, so the next question would be that how do we visualize this on a graph paper or on a graphical, if we had to do a graphical analysis, what are we supposed to look at? So let's say this is the temperature scale and this is our zero scale, for example, temperature, and this is time in seconds. So what have we done is that we started from this temperature, that is 20 degrees centigrade. We started heating it up, and then we observed that at a certain point it became constant. The temperature did not change and the line became horizontal. So what's happening at this point? We realize that the time is passing by. For example, this could be 5 minutes, 10 minutes, 15 minutes. The time is passing by, but the temperature is not changing, right? Because at that point, the state change is taking place. It's converting from liquid to the respective gas. Okay, so there's going to be some amount of time spent so that it eventually does convert its state. But once every last atom of the liquid has converted into gas or has boiled, it will start gaining temperature again. So for the sake of question, our last point where we concluded our system was 150 degrees centigrade. Now, for the sake of question, or for the sake of just looking at another extreme, since we have already moved from the boiling point stage, or we have already concluded the last state of matter, no matter how much temperature you increase for water now, or for gas or steam now, you will never see the horizontal line again, because after becoming a gas, there is no other state of matter, at least for this situation. So for this section, when we were experiencing a change of state, we used the formula mc delta T, and it was still a liquid at that point. Over here, it was a liquid plus a gas, a mixture of both, and we used the formula mLV to calculate the energy. For this part of the question, it had entirely become a gas, and we used the formula mc delta T. Do we understand this?
Yeah.
Yes? So
Yes.
if the examiner gives you a question in P1 or P2 and asks you to find out the melting point or the boiling point of any system, of any substance that he may give you in the question, what you're supposed to look for is that if it's a melting point or a boiling point, it will be a horizontal line. It will be a horizontal line. So let's try to look at it from another perspective. Let's say that we were starting from this is my 0 degree centigrade line, and we had to melt ice, right? So let's say that ice was at minus 10 degrees centigrade and we had to heat it up to 200 degrees centigrade. This is our final target, right? So we start at something below 0, that is minus 10. We heat it up, it reaches its melting point for the first time. It stays in that temperature range because a change of state is taking place and the bonds are being broken down. There is no increase in kinetic energy, there is no increase in temperature. Then, when every last solid particle of ice has converted into respective liquid or water, then if you continue to heat it up, or it continues to absorb energy from the surrounding, just the way that you put a piece of ice on the table, and it will melt away eventually because it's absorbing energy from the surrounding. So it can happen automatically as well, and sometimes you do have to give energy from the external environment. How do we do that? For example, if I had asked you to melt iron, then you would have to inject or give more energy that is already available in the environment, right? So it depends on from substance to substance. Okay, so at this stage, we believe that at some point in time, it has converted every particle, or every particle of ice is converted into liquid. And now, if we keep on providing the energy, it will increase its temperature up to its boiling point. So we see the very first time the temperature becoming constant again is on its boiling point. So for some time, the line becomes horizontal again. Now, since our final target was 200, I believe we would still be heating it up. So after every last molecule, I keep repeating the statement because that is the actual concept. After each last molecule, or every single molecule of liquid has not converted or has eventually converted into gas, until that point you will find the temperature to be constant. So after every liquid molecule has converted into gas, which means that every bond has been broken, now if you keep on providing energy, you will see that the temperature keeps rising up to, of course, the final temperature that you want the question or you want your scenario to go to. So this point will be 200 degrees centigrade. Now let's write down the respective changes in states, their respective situations and formulas. If we had to find out the total energy, how would we have done that? So over here it's a solid, over here it's a solid plus liquid, over here it's a liquid, over here it's a liquid plus gas, and over here it's a gas. So at this stage, since there is a change of temperature, there will be mc delta T. Over here mc delta T, a change of temperature. Even for gas, mc delta T, because between the same state you can have a change of temperature, right? So when it reaches its melting point, we use the formula MLF, latent heat of fusion. When it reaches its boiling point, we use the formula MLV, vaporization. So if you had been given the question that ice has to be melted or ice has to be heated up from -10 to 200, what students generally do is see this or identify this as a change of temperature and directly apply mc delta T just once, mc, and just randomly select the value of water and put in 210 as their answer and give the final answer. It's your job to identify that for this system there will be two changes of state. We cannot use mc delta T directly. There will be multiple stages involved in the process. So breaking this down or breaking down the question is up to you, or is your responsibility. So -10 degrees centigrade goes up to 0 degrees centigrade, stays at 0 degrees centigrade as the change of state is taking place, then goes up to 100, stays at 100 because change of state is taking place, and then goes up to the final temperature that you actually designed the system for. So from -10 to 0, I see mc delta T. The only change that I observe is that it is solid, still solid. Here it becomes a liquid, still a liquid. Here it becomes a gas, and still a gas. Wherever you see a change of state, which is of course going to take place at their respective melting points or their respective boiling points, is where you use the formula MLF and MLV. You will find in your marking scheme that this is what they write down now, ML only, and they just leave it to your understanding that you just pick up the right value, right? And for the other sections where we see a change of temperature, that will be mc delta T, mc delta T, with one special care that the value of C over here should be for a solid, the value of C over here should be for a liquid, and the value of C over here should be for that respective elements, gaseous state, liquid state, and solid state. In the question we have been discussing is generally for water, but that could be asked for any other substance. Could be asked for iron, could be asked for aluminium, could be asked for wax, could be asked for a gas. It doesn't matter. Do we understand this point? Any issues up to this?
So basically, for example, you have -10 to 200 degrees Celsius.
These are two different things. I repeat my statement. Change of state is breaking of bonds. Nothing more than that. Change of temperature is change in kinetic energy of the molecules. As previously discussed, that you must keep this point in mind, that the temperature of all the universal substances, even in the whole universe, temperature of a substance would mean directly or is directly related to the kinetic energy of its particles, be that a gas, be that a solid, be that a liquid. And one interesting thing that you would discover at A levels, that is why I enforce this point again and again, is that this equation does not matter or does not discriminate between the states of matter. It doesn't care. So, for example, if we had water at 50 degrees centigrade and we had a piece of iron at 50 degrees centigrade, although they belong to different states of matter, the kinetic energy of their particles would be the same. It would be the same because they have the same temperature. And of course, if you open up the formula, it's against intuition, but let me explain what you might be getting confused about. If you open up the formula of half mv square for both of them, I'm saying that they have same energy. So let's say that they have 10 joules of energy for each molecule. Okay, acceptable, that's fine. But what's the difference? Because water molecule is a lighter particle, or appears to be constituent of hydrogen and oxygen, and iron is Fe, which has a molecular mass of 56. Then where would we see the difference? We will see the difference in the relative speeds, because if a particle is more massive, you will find it moving at a slower speed. If a particle is less massive, you will see that moving at a higher speed. But putting in all the values, it will always give you the same answer if they have the same temperature. This is the importance and significance of this equation. This is one of the laws of thermodynamics that actually helps us to elevate, or to be elevated at least, from the states of matter and get into a more abstract understanding of this, that we don't care about the specific mass or velocities. What we care about is, if we know the temperature, we can predict the kinetic energies of those particles. And of course, if you dig deep down, if they have different masses, they will also have different velocities. But since you put it in the formula of half mv squared, you will get the same answers if the temperature is same. Do we understand this point? Right? So this is one of the ideas that will be broadly discussed. It will be discussed in very much depth. There are 2 to 3 chapters in second year of A levels. That is why I keep enforcing this point. Do not forget this idea. And over here, when I keep saying that there is a change of temperature, then of course there is a change in kinetic energy of the water molecules. They will be more agitated. They will be having more velocity. Even here, of course, we understand that the water at 100 degrees centigrade and water at 0 degrees centigrade, the difference that we feel in their temperature is because of the kinetic energy difference. So if I put my hand into 0 degree centigrade water, I will feel it to be very cold. If I put my hand into 100 degree centigrade water, God forbid, that will be very dangerous, and that will eventually be a hazardous situation. So how do I feel, or how do I visualize this change in temperature at a molecular level? I should visualize, or I should observe, that molecules at 0 would be moving at a slower speed, and molecule at 100, or a particle at 100, would be moving at a much faster speed, because they would have a higher energy content. So speed and kinetic energy will always be interlinked and eventually linked with the temperature of that substance. Do we understand up to this point? Any issues?
Yeah, I understand.
So okay, so one last thing about this, that since we are trying to heat up the situation, what we have done so far is trying to heat up substances at their boiling points, beyond their boiling points, and so on and so forth. These tasks have to be achieved by some electrical heaters, right? Or even if they have to absorb energy from the surrounding, they have to absorb some energy. So this energy has to come from somewhere. So to include that concept that we already done in work power energy, the examiner would give you this question, that find out the power of electric heater that would do this for you. So let me write down that question, that find power of electric heater that will bring about this change, let's say from 20 to 200, not my problem, not my concern, that will bring this change, or do this task for you, right, within, let's say, a matter of 15 minutes. So we have done the formula for power. We want to find power, so power is equal to energy divided by time taken for the process. And to find energy, we say basically the definition is work done by time, but since work done is also joules and energy is also joules, we can use the same formula. And over here, if you can mimic, or if you can at least say where the work is being done, you can say the work is being done to increase the kinetic energy for temperature change, and the work is being done to break the bonds so that the state of change, or the change of state, could occur. So wherever you go, you will find work done in some form or the other, but I generally generalize this system, or this equation, to energy over time. Because by the end of the day, if you want to do some work, you need energy to do that. So it's basically the same thing. Okay, so we found the energy in the previous part for a certain process to go from 20 to 150 as 19 power 6, right? 19 into 10 power 6 joules. And this task has to be completed in 15 minutes, right? So I will use 15 into 60 to convert this into seconds to eventually find my answer in watts. This is how we actually design our electric heaters and air conditioning systems for large buildings. That we know how much energy is going to be produced by human bodies. We know how much heat is coming from the outside. We know the amount of energy that still needs to be removed from this space so that eventually it feels colder or warmer. And we also have a set target given to the manufacturer that we want it to be cooled down very quickly, within 5 minutes, within 2 minutes, or within 15 minutes, depending upon the budget, depending upon the economics of it, depending upon how much you're willing to spend. This is how they're actually designing their systems at the back end. Do we understand the larger implementation or the larger idea of this topic? Where is it actually helpful?
Mm. Yeah.
Similarly, similarly, you will find this idea being utilized in designing radiators for cars as well, because radiators are removing energy from the system, from the engine block. So they also design the movement of the water, how much water is required to be moving from the system for how much amount of time, so that it can eventually move that amount of energy. And they use the formula mc delta t. So they think, for example, that water entering the engine is at, let's say, 50 degrees centigrade, and the water leaving the engine is at 80 degrees centigrade. So if I want to make sure that the engine never crosses 90 degrees centigrade, how much water needs to be flushed, or how much water needs to be continuously provided to the system or to the engine so that it never occurs. So what are we left with? mc delta t divided by time. So this is what basically the engineers are trying to calculate. How much mass need to be flushed through the engine in a respective time. That is how they design the water pump of the engine, that this is the amount of water that needs to be continuously running from the engine so that this worst condition never occurs. Do we understand this point? Right? So this is again the formula for Q. This is time again equating to power, and then the power of the water pump or the oil pump or whatever auxiliary components are connected to it can be designed by the manufacturer. Right? So this is the larger end, you can say, or the large